Hi guys, we're going to take notes today for linear motion, which is chapter 11 in your textbook. Make sure we're taking Cornell notes, so your title should be linear motion. Make sure whenever you come to a new header in the notes that you make a new section. So on the left side you should be writing those headers, the right side should be taking the notes, and then you should also be including questions and a summary when you're finished. Today we're just going to do 11.1 and 11.2, so we'll talk about distance and displacement and speed and velocity. So we're talking about pretty much this whole semester we'll be talking about some sort of motion. So we're going to start off pretty easy here in chapter 11 and talk about just some really simple concepts like distance, displacement, speed, velocity. So when we talk about that, we need to make sure we know that when we are looking at how fast or how slow something's moving, it's really relative based on where you're located at. So if you're on a train, say, and you're on a platform and you're watching that train go by, it's going to look like it's going pretty fast depending on how fast it's moving or slow it's moving, but you're going to see it moving. If you're inside the train and you're watching the platform go by, that's also going to look like something's moving relatively quickly, but for that it's going to look like the platform's moving and you're sitting still. If you're inside the train and you're looking at the ground, nothing's going to look like it's moving because you're in the moving object. So depending on what you see moving or what appears to be moving is really based on your frame of reference because of the relativity of where you're at. So two concepts here, distance and displacement. These are two big vocab words. Distance is the length of a path between 2 points. Doesn't have to be a straight line, and we measure it in meters. So you can walk a few paces north and then a few paces to the east and then go and make a U-turn and go back to the west, and all of that distance that you travel is going to be covered under distance. Displacement is, however, would not be. That's just the length between where you start and where you ended. So depending on how much you walked, if you ended up as the same place as you started, your starting point and ending point would be the same, and you wouldn't have a displacement. So displacement is just the straight line distance between start to end. And displacement also, you have to include a direction. So it's really important that in displacement, you're talking about a length from start to finish, straight line, but also a direction. So I ended up 5 meters west, or I ended up 20 meters east. That's important with displacement. Okay. Displacement is something we call a vector, and a vector is just a quantity that has a magnitude, meaning something that can be big or small, like I walked 2 meters versus I walked 100 meters. So that's a big or small quantity. And it has a direction. So it has to have a magnitude and a direction. And we're going to talk about another vector later on, but vector just quantifies something that has both a magnitude and a direction. And we categorize that with arrows. A vector we draw with arrows. So displacement, remember, has to have a distance and a direction. So if we're not looking at direction right here, or distance, we're only looking at displacement. So if we're looking at displacement between these two scenarios, I have a car that's driving, it drives 4 kilometers, it stops, maybe it's at like a red light, but then it goes 2 more. So displacement is just the distance from start to finish. So I started here at 0, I ended at 6, so my total displacement is 6 kilometers. If we look at scenario B, I start at 0, I drive 4 kilometers, but maybe I realize that I forgot my phone at home. So I turn around and I drive 2 kilometers back. My distance from start to finish, now my start is here, but my finish is here. So how far am I away from where I started? I'm only 2 kilometers. So the difference between distance and displacement is distance is that total, both would have the same distance, 4 plus 2, but the displacement's different because on one I went in the same direction, the other one I went back. Okay, so if displacement isn't along a straight line, all you have to do is make the straight line, and then if it's a right triangle, you can do Pythagorean theorem, which is a squared plus b squared equals c squared, or if it's something like, each grid is like a centimeter square, you can measure it. That would be fine too. So here are a few problems here. I'm going to do one together and I'll have you guys just do the second one by yourself. But in this scenario, we have David walking 3 blocks north, and then he turns and walks 4 blocks east. So write that scenario down and draw a little grid in your notes, and we'll do this together. So I'm going to go to the next slide, and I'm going to draw that. So drawing that, I have David, and he can start anywhere because I don't know where he's at, but I want to make sure I leave enough room for him to walk what I said. So David's going to start here, and I'm going to do this with my ass here, and he's going to walk 3 blocks north, so 1, 2, 3, and he's going to walk 4 blocks east, so that's this direction, 1, 2, 3, 4. Okay, so David started down here, he ended here. What distance did he do? Well, he walked 3 plus 4. So I know my distance is going to be 7. But my displacement's just that straight line between start and finish. So how do I figure out this one? Well, I could do the Pythagorean theorem. 3 squared was 9. 4 squared is 16. So 9 plus 16 is 25. Square root of 25 is 5. So I know that my displacement's going to be 5. But which direction did I travel? I traveled northeast. So my displacement's actually 5 meters or 5 centimeters or whatever northeast. Okay, so here's another scenario. Go ahead and pause it, write it down, and map that out. And we'll talk about in class what you guys got as the answer. But I'm going to move on to 11.2. So if you needed to pause at that point and go back, that's probably a good idea. 11.2 is speed and velocity. Speed and velocity can often be confused as the same thing, but there's a distinct difference between the two. So we'll start with speed. Speed is the ratio of how far you went divided by how long did that take you. So it's distance divided by time. We usually measure that in meters per second. There's 2 types of speed. I could talk about average speed, which is just your entire trip. How long total did you, how far did you go total divided by how long did that take you total. That would be average speed. Instantaneous speed is just at any particular moment in my trip, how fast am I going? So if you asked your mom at any one point, hey mom, how fast are you going right now? And she'd say 60 miles per hour. That instant, that would be an instantaneous speed. Here is a formula for average speed. Again, it's just total distance divided by total time. We'll use this formula a lot and do some calculations. I'm going to skip that. So when we graph speed, we just graph distance versus time. Time is our IV, distance is our dV. And depending on how steep that line is, if it looks like it's like a vertical straight line or closer to a horizontal straight line, however that slope is, that's going to tell us relative speed. So things that have a steeper slope or almost look more vertical are going to be faster. Things that are slower have that almost horizontal or lower slope or slower slope. Velocity is different than speed in the fact that it is speed, but it also adds a direction. So if I want to say what is the velocity of something, I have to say 5 miles per hour east. I have to add that direction. So velocity technically is speed. You can calculate it the same way, but you add the direction on it and that makes it velocity. Because it has a magnitude, again, a big or small number, I'm going 5 miles per hour, I'm going 100 miles per hour, that's a magnitude. And a direction, it's a vector. Again, a vector is something with an arrow. Or we make it look like an arrow, and it's just something with both a direction and a magnitude. Change in velocity can be because you changed speed, so you went faster or slower, or because you changed direction, or because you did both differently. And last thing I want to say here is about vectors. So when we're representing what a vector is, we're going to do this in class a little bit, but a vector is represented by an arrow. And so those arrows are obviously different. One's bigger, one's smaller. The bigger arrow could represent I'm going a longer distance, or maybe it represents I'm going a faster speed. The shorter arrow represents a shorter distance, or maybe it represents I'm going a slower speed. But whatever vector we're talking about, if it's going to be velocity or displacement, shorter arrows obviously going to mean I'm going less, either slower or less distance. Bigger arrows going to mean I'm doing something like either faster, walking more, traveling more. Okay, so that is your notes for 11.2 and 11.1. Go ahead and write your summaries, write your notes, your questions, and I will collect these in class, and we will most likely have a quiz over them as well. Okay, bye guys, thank you.